Does anybody have homework questions in 3.3? Anybody have questions to go over? I want to bring your attention to some class activity material that you'll need. So if you go to Canvas, there's a tab that says class activity materials. And we'll need, starting Wednesday, we'll need the Pythagorean triangle pattern. So if you haven't enjoyed the material so far in the math class, we'll be doing something quite different in the future chapters. Okay, so the next chapters are more geometrical. In fact, we're starting with the Pythagorean triangle templates. So these are formed from 3x5 cards, and you would print the template out off of Canvas and slice your 3x5 cards on the diagonal. So that one you don't really need the template for, but for this square you do. So this square is the correct size to go with these 4 triangles that you'll get when you cut those apart. Okay, so print that and cut it apart, please. Otherwise, class will be very boring for you on Wednesday. You won't be able to participate at all. Also, on the class activities, you see directions for the platonic solids. So it's time to begin working on the platonic solids. These are platonic solids right here. Each of their faces is the same. So this platonic solid, a tetrahedron, is made up of 4 triangles that are all exactly the same. This is a cube. It's made up of 6 squares that are exactly the same. This is an octahedron. Okay, so you're going to make these, and this is the section. This is 4.5, you making these. So you figuring them out and holding them and looking at them and constructing them and examining these historical shapes is what most of 4.5 consists of. So try and take 1.5 hours or 2 hours and construct these. The way you construct them is from chenille sticks and coffee stir straws. You can buy those as a kit at the bookstore for $4, or you can get your own chenille sticks. They're just pipe cleaners and coffee stir straws. Then you cut them up into fourths or thirds. This suggests 2-inch segments. All your pieces should be the same length. A little smaller is easier, so cut them into thirds or fourths would be easier than halves. And then you kind of bend the chenille sticks so they'll hold together the stir straws. Here, I'll show you on the overhead. So here's one that I made. This is the octahedron. It's 4 triangles all put together. So the triangles are all the same size because I cut my stir straws to be all the same size. You can make them a little smaller than this. Smaller is easy to carry around in your backpack because you're making 5, and so if you use smaller pieces, it's a little easier. You see the chenille sticks at the end there holding the stir straws together, okay? Okay. So like I said, that takes 1.5 hours or 2 hours, so that's why I'm telling you now, so that you can pick a time to do it and not be trying to do it the night before or that morning. Any questions on the platonic solids or the Pythagorean template? Okay. Commercial for your study group today at 1 to 2, Wednesdays 4 to 5. If you can't make study group, you can have one-on-one tutoring as well. And if you can't come to campus, I sent everybody out an email earlier in the semester that was all the online students about Skype tutoring that's available. So you could sure contact me again if you lost that email and you want to do tutoring. Now, quiz 1, I do not hand back quizzes because our material is not cumulative. You're not going to get quizzed on quiz 1 material again, and so I don't hand those back. But if you want to know how you did, you're welcome to stop by my office. Online students, you're welcome to email me, and I'll send you back how things didn't work out if they did not work out. There were some very fine grades, by the way. You should pat yourselves on the back. Okay. the proofs ended up being about 9 points each. So there were 3 proofs on the handwritten part. One for rational, showing there were infinitely many primes. One for showing that a particular square root was irrational. And the other one that was 9 points was writing a repeating decimal as a fraction. So those were 9 points. And if you just lost 9 points, you probably didn't remember one of those. Any questions before we begin? Then let's continue in 3.3. We're looking for an infinite set bigger than n. Does anybody remember if we found an infinite set bigger than n? Anyone remember if we did or not? Well, let's talk about it some more if no one remembers. So n was the natural numbers. For a set to be larger than n meant that it can't be listed. I'll make this a little bigger. So a set that has the same cardinality as n a set that has the same cardinality as n can be listed. Because a set that has the same cardinality as n can be put into a one-to-one correspondence with n, and that comes down to listing it, because you can list n and then if you have a set that can be put into a one-to-one correspondence with n, you can list that next to it and make those double arrows to show the one-to-one correspondence. Does anybody remember the set we found that we could not list? Yes?
Real numbers?
Good, yes, the real numbers. The real numbers we'll use the R with the double bar to abbreviate. The real numbers cannot be listed. Real numbers cannot be listed. The real numbers have a larger cardinality than the natural numbers. The real numbers have a larger cardinality than the natural numbers. Remember, the real numbers are all the numbers on the number line. All the numbers on the number line. So the rational numbers, the irrational numbers, the square roots are some of the irrational numbers, fractions, decimals, whole numbers, all the numbers that you know, all the ones that do not have an I in them. Those are the real numbers, and they cannot be listed. They have a larger cardinality than the natural numbers. So with these different, that means there's more than one size of infinity, which is counterintuitive. The life lesson in this section was to consider the counterintuitive, and that is what the father of set theory did. George Cantor, whose picture was on the screen at the beginning of the day here. Your author has a little bit more to say about him. So the underlined portion in your text, but for those mathematicians who were deeply immersed in such issues, the idea of having many different infinities was a tremendous blow. Out of vague and ill-defined notions of sizes or of sets, Cantor distilled the fundamental idea of one-to-one correspondence. This idea is so basic that one feels compelled to accept its logical consequences. But these consequences contradict the intuition of most people until their intuition is adjusted, after which the concept of more than one infinity becomes perfectly natural. Thanks to Cantor, who reached out and considered the counterintuitive, no mathematician today has a problem encompassing the idea of multiple infinities. So the way we looked at finding these multiple infinities was to find a missing number. And we're going to do that again today. We're going to look at the list in your textbook, and then we're going to construct a missing number. So this is a proposed list. If you could list the real numbers, it would look something like this. But then we're going to find that you can't list the real numbers, because we're going to find a number that it's impossible to have on this list using our dodgeball proof. So that will be good practice for your quiz eventually, and that's why I wanted to look at that again. So let's write this out as we would on a quiz. So demonstrate your understanding of Cantor's dodgeball proof. No, he does. I might put dodgeball on the quiz, okay, just as a reminder. But it's Cantor's diagonalization proof. Demonstrate your understanding of Cantor's diagonalization proof by finding M, which is not on the list. This time we'll use 2 as your default. Use 2 as your default digit, otherwise use 4. Use 2 as your default digit, otherwise use 4. So you'll get told on your quiz which digits to use, and you'll be presented a list similar to this one that you see in the text. So in fact, I have to turn this upside down to fit it on the screen here. Is that fuzzy? So start your number out with 0 point. Okay, because we're looking at our decimal expansion. Remember, every real number has an infinite decimal expansion if you care to write out all the decimals, even if it's just ending in zeros. And so we're going to focus on the decimal places. So we look at the real number that goes with the natural number 1. And we say, well, we're going to be different from that real number in the first decimal place. We're going to use our default digit 2, because the number 5 is not a 2. So I'll use my default digit 2. Then when I look at the second decimal place for the number I'm making, M, I go to the second number, the one that corresponds with the natural number 2. And the second real number has a decimal place in the second position of a 2. So now I go to my default 4. I'm sorry, I can't use my default 2, so I go to my the alternate 4. Okay, because now I'll be different than that row.
Wait, why did you get? How did you get 4?
So on a quiz, it will tell you which one to use as your default. So this time we're using 2 as a default, otherwise use 4. So you'll get told which digits to use. So you always use the default one unless that digit is the number, because we want to be different. We want to be different from every single number on this list. So now I'm going to be different from the second number on the list in the second decimal place, because I'll have a 4, not a 2. And then the third number has a 2 in the third decimal place. So to be different from the third decimal place, I can't use my 2, I have to use a 4, the alternate number. So I'm always using 2's here, except if it is a 2, then I use a 4. So in the fourth row, I look at the fourth decimal place. And that's again a 2. So I'm going to use a 4 so that I'm for sure different than the fourth decimal place in the fourth row. And in the fifth row, I'll be different from the fifth decimal. 1, 2, 3, 4, 5. So there's a 3 in the fifth decimal place. So what would I pick? 2, my default. Yeah, I can use my default there. So now I know I'm different from the fifth number. Now the sixth number, 1, 2, 3, 4, 5, 6. There's a 2 there. So I can't use 2. I'll use a 4. So that was the sixth decimal place. It's going to be a 4. So it's not going to match the 2. Seventh decimal place is going to be 3's. So I can use my default number, which was the 2. Eighth decimal place in the eighth row, 1, 2, 3, 4, 5, 6, 7, 8. That's a 2. So I'm not able to use my default 2. I'll go to the 4. Now I'll put ... for the 9 and 10. I don't know what's there. But in the 11th row, I can look at the 11th decimal place. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's a 2. So I'm going to go to make a 4. Yes?
I'm confused on what this helps us find.
Good. What does this do? What this does is we've created a number, even in the ... we know M will not be on the list. So we have a method of proceeding here that guarantees us that we've found a number not on the list. Because we know it's not on the list because it differs from the first row in the first decimal place. It differs from the second row in the second decimal place. It differs from the third row in the third decimal place, and so on. So we know that this number M is not on the list. Is that part okay? Are you okay with that number not being in the list, even in the ... because we use the same pattern?
What does this pattern mean?
So this pattern guarantees we're not going to match any of those rows because we'll always differ in one decimal place. So if there was a list of real numbers, if someone said, wait, no, the real numbers are of the same cardinality as the natural numbers, here's my list, we can say no, because look, here's a number that's not on your list. That's impossible. You could not have made a list of real numbers in a one-to-one correspondence with the natural numbers because you did not get this number on the list. You missed one. Remember, a one-to-one correspondence can't miss any and can't use any twice. So this is a number not on the list.
Is this Cantor's proof?
Yes, we're going to actually make the proof. This is an example of Cantor's proof. We're going to make the proof next. So I just wanted you to understand the proof before we write it down, because a proof works for all lists, right? This list is all specified. A proof has to work for all the possible lists of real numbers, not just one that's written out that we can look at. So that does bring us to the proof. So any other questions before we tackle the proof itself? Okay, let's write down Cantor's diagonalization proof. Cantor's diagonalization proof that the real numbers has a larger cardinality than n. Cantor's diagonalization proof that the real numbers has a larger cardinality than n, the natural numbers. So like so many of our proofs, we're going to do a proof by contradiction. Suppose that there is a one-to-one correspondence. Suppose that there is a one-to-one correspondence Suppose that there is a one-to-one correspondence between the natural numbers and the real numbers. This is fixed. Okay, so there is this one-to-one correspondence. Someone found it, we fixed it, there it is. Now we're going to create the missing number. Let m equal 0.d sub 1. We put these little subscripts, okay, to indicate which decimal place we're on. So decimal place 1, decimal place 2, decimal place 3, decimal place 4, and dot, 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 because this is a real number whose decimal expansion therefore can be written forever. And now we create the number itself. Let decimal 1, whoops, that's let, not led. Let decimal 1, d sub 1, be 2 if the real number corresponding to the natural number the real number corresponding to the natural number 1 has a first decimal place that is not 2.
And the natural numbers are what you count with, right?
Yes.
And then real numbers are all the numbers on the number line?
Yes. The natural numbers are what you count with, and the real numbers, all the numbers on the number line. Otherwise, d sub 1 is 4. So we're creating the digits. Okay, so otherwise d sub 1 is 4. So this first decimal place d sub 1 is going to be a 2 if the real number that corresponds to the first natural number has a first decimal place that is not 2, just like what we were making. Otherwise, d sub 1 is 4. Now we write that again, only we move on to the second decimal place. So just the decimal places change, okay? Let d sub 2 be 2 if the real number corresponding to the natural number two has a second decimal place that is not 2. Otherwise, d sub 2 equals 4. Let d sub 2 be 2 if the real number corresponding to the natural number 2 has a second decimal place that is not 2. Otherwise, d sub 2 is 4. Now we could keep doing that forever, so instead I'm going to say continue because I believe the pattern is established. So, m is not on the list. So M is not on the list. Okay, we're supposed to have a list of real numbers in a one-to-one correspondence with the natural numbers, but we've just found a number M, a missing number. It's not on the list. Not on the list of R. So there is no one-to-one correspondence. So there is no one-to-one correspondence. Between the natural numbers and R. There is no one-to-one correspondence between the natural numbers and R. It's impossible. If you think you have such a list, we can come up with a number that's not on the list. So the cardinality of R is larger than the cardinality of N. So the cardinality of R is larger than the cardinality of N. So this proof is pretty long. Takes some thought. We're looking digit by digit. I don't expect you to repeat the proof on a quiz. You'll be happy to know that. So on a quiz, what I would expect you to do is to do two things from this section. One thing is to take a list like this and come up with M, the missing number, so demonstrate your understanding of the proof, even though you don't have to write the proof out, by coming up with the number M. And the other thing I'd expect you to do, you could make an example of on your first page of notes this morning, to demonstrate a one-to-one correspondence between two lists. So we started writing N out. Why don't we write out another, how about the evens, 2N. And I would ask you to demonstrate a one-to-one correspondence between N and 2N. So you can go ahead and do that. You probably have space on your notes for that. So one of the things that, there are some very fine students in here, but some of you I'm concerned about. And one of the things that you would want to emulate if you weren't doing so well was to always know what you're studying, what you need to know. And so that's why I'm telling you, okay, so try and put little notes, little highlighters in your notes where there's material I say you need to know for the quiz, okay?
So this is something we need to know. Even though we don't have to like write it out for the quiz, we still need to.
So you don't have to repeat that proof that we just did with all of this B sub 1 and B sub 2 business, but you do need to be able to come up with the missing number given a list. And you do need to be able to do this. So hopefully you wrote down the evens, and you put dot, 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 showing the list goes on forever, and you put double arrows to show the one-to-one correspondence that you've established. Okay. None are missed, none are used twice. Anybody have any questions there? Then let's move on to 3.4. So we found one set. Wait, I don't think, that's not the question. Where did my other question go? This section has two questions. There's my question. Okay. So 3.4 begins with a question. Is there an infinity bigger than the real numbers? So go ahead and write down what you think about that. I'll write down the question too.
Like any infinity or like a numerical infinity?
Any infinity. So you have two sizes of infinity so far. The natural numbers and the real numbers. Every other set that we've looked at was the size of the natural numbers, except for the real numbers. So the question in 3.4 is there an infinity bigger than the real numbers? So go ahead and write down what you think, yes or no, and we should answer that by the end of the section. We're going to begin by creating sets of sets. Sets of sets. So back to finite. We always start with finite before we go to infinite. Make sure we understand finite well. We're going to make a set S for suits of the suits of cards. So hearts, diamonds, clubs, spades. So here's our set S. And what we're going to do is think about all the sets that you can make out of those four elements. All the different collections you can make out of the four elements. So, for example, you could make a heart and a diamond. That could be a set. You could make diamonds and clubs. You could make hearts and diamonds and clubs. Well, let's just go ahead and make all the sets we could make. So I think I could make more sets of 2 or 3 elements. Let's see, hearts and diamonds, diamonds and clubs. We could have clubs and spades. We could have hearts and spades. We could have hearts and clubs. Okay, I have hearts with everything. I don't think I have diamonds with spades. Let's put diamonds with spades. Do I have clubs and spades? Yeah. Okay, let's look at other sets that have 3 elements. We could have diamonds, clubs, and spades. We could have hearts and diamonds and spades. So here I have a set with no spades. Here I have one with no heart. Here I have one with no club. I didn't do one without diamonds. Let's do one without diamonds. So hearts, clubs, and spades. Am I missing any? Well, we didn't do any that have just one element. We could make 4 sets that each have one element in them, right? So we could make one with hearts, a set with hearts in it, a set with just diamonds, a set with just clubs. So we're finding all the sub-collections in our collection here, and a set with just spades. We didn't make the empty set. We could have, when we're thinking of all the different ways we could collect the elements in our set, we could just have nothing in it. Or we could have all of the elements in the set. So what we do is we put all the collections that we can make out of the set of hearts, diamonds, clubs, spades. We put all the different collections together into one big set. So I'll put a big set brace to the left, and then I'll put commas between. I think I have some commas. I'll put commas between my subsets here. And what I've made then is a set of sets. Put a little ending brace there. I made a set whose elements are sets. So this actually has a name. This is called a power set. It's usually written with a cursive P, for power set, and then you put in parentheses the set name that you're making all these sub-collections from. So it's a set of sets. Each element in this power set is itself a set. And we made the power set is all the different sets you can make out of the set S. That's the power set of S. Let's try one that's not so big. Let's try something with just 2 elements. That will be easier. So how about we do a set C for computer. C will be Mac and PC. Then we'll go ahead and make the power set of computer set. So we're going to put a collection of all the sets I can make. So we could just have the empty set. Or we could have sets with just one element each. So a set with Mac in it, and a set with PC. Or we could have 2 elements. The set with Mac and PC. So we made all the different collections that are possible out of the set Mac and PC. And put those together in a collection. So that's our power set. How about you try this? Try this with A, B, and C. So that will be L for letters, okay? And you have A, B, and C. And go ahead and make the power set of L. And I'll walk around, and probably Nicholas will walk around, and we'll see if you're getting the hang of this. Find all the subsets that you can here.
Do we have to take a photo of anything for like in classes on?
Not today. Raise your hand if you're stuck. How many elements did you get?
7.
Anybody get any more? Get more? Okay, so should be 8. So there's the empty set, there's the set with all A, B, and C, the 3 sets with A, B, and C, and then the 3 sets that have just 2 elements, AB, BC, and AC. Well, we could do the same thing with the natural numbers.
They go on forever.
Yeah, that's true. Since the natural numbers is an infinite set, the power set of the natural numbers would go on forever. So we're not going to write all of those, but we can write some. So let's go ahead and write some down. So in our power set of the natural numbers, we could include the empty set, and we could include the natural numbers themselves. I don't know why the computer keeps going fuzzy. It's really strange. Well, we could include evens. We could include some finite sets. We don't have to have all infinite sets. We could have some finite sets, like 1 and 2, 3 and 4. We could have 10, 20, 30. Oh my goodness, it's just like an endless number of sets that we could make, isn't there? Yeah. Okay, so I'll just put ... and go on. Well, notice that these power sets look like they're larger. The cardinality of the power sets looks larger than the cardinality of the sets. The cardinality of the power set of S looks larger than the cardinality of S. So let's go back and look at the cardinality of the different size sets that we had. So we'll look at the set size and look at the power set size that went with that. We started with the set S, the set of suits, and there was 4 elements: diamonds, hearts, clubs, spades. In the power set of S, what do we have? Anybody else get 16? Okay, good. And then we had the set C for computers. There were 2 elements in there. And the power set of C had 4 elements. And then we had the set L that had 3 elements. That's the one you worked on. And the power set of L had 8 elements. And then the natural numbers, you can see there's more. That's hard to tell with the natural numbers. We know that now. Even though something looks like it's more, it's not necessarily easy to see if there's more, is there? So we'll come back to that idea. Let's do just one more. So we have a set a size 1. So if we have a set I'll call B, and it just has the number 1 in it.
Can you roll it down?
Thank you. What would the power set of B have? Good. Because it'd have the empty set and the set with 1. So that's 2. So does anybody see a pattern here? Between the size of a set and the size of the power set.
Power set's always bigger.
It is. It's always bigger. It's strictly bigger. It's not just big, greater than or equal to. It's just greater than.
Does that keep doubling?
It does keep doubling. Yes, it does. Good. It doubles. So in fact, the 2 is 2 to the 1. The 4 is 2 squared. The 8 is 2 cubed. That's another way to say you're doubling. You multiply it by 1 more 2. Okay, so 2 times 2 is 4. Yeah. Thank you. And 2 times 2 times 2 is 8. So doubling is exponents are another way to express doubling. But that way it's kind of nice because then you see the exponent is the size of the set. So that's Cantor's power set theorem. That the set is bigger, but we'll write it out a little more carefully than that. Cantor's power set theorem. For any set S, finite or infinite, for any set S, finite or infinite, the cardinality of the power set of S cardinality of the power set of S, P of S, is strictly greater than the cardinality of S. For any set S, finite or infinite, the cardinality of the power set of S, P of S, is strictly greater than the cardinality of S. That brings us back to our question that we started the class with. Is there an infinity bigger than the real numbers?
Yes.
Yes, good. And what would be one example of a set that had a cardinality bigger than the set of the real numbers?
The power set of real numbers.
Yeah, the power set of real numbers. So the power set of the real numbers has a cardinality greater than the cardinality of the real numbers. The power set of the real numbers has a cardinality greater than the cardinality of the real numbers. So we know several sizes of infinity now. There's not just one size, and you know several of them. You know some that we'll denote here. So we'll arrange these in increasing size. We have the natural numbers, okay? We had lots and lots of sets that were in one-to-one correspondence with the natural numbers, but then we found that that cardinality was less than the cardinality of the real numbers, and now you've correctly told me that the power set of the real numbers has a cardinality greater than the cardinality of the real numbers. What would be a cardinality bigger than the cardinality of the power set of the real numbers?
Is there one?
Anybody have ideas? Yes.
Power set of the power set.
Perfect. Yes, that's right. The power set of the power set of the real numbers. Because this is a set. The power set of the real numbers is a set.
You can have a power set of the power set.
You can. And you can try writing it out and it's messy and yucky. No, we're not going to either. But you can try writing it out. It's a good exercise. Well, one thing we didn't fit in here is the power set of the natural numbers. Where do you think the power set of the natural numbers falls in here?
Right before, like in between the real numbers and the power of the real numbers?
That's a good guess. It turns out to be right here. It's actually exactly equal to the power set of the real numbers. The power set of the natural numbers, I'm sorry, I misspoke. The power set of the natural numbers is exactly equal to the cardinality of the real numbers, which is curious. So the real numbers can be put into a one-to-one correspondence with the power set of the natural numbers, that group that we started to write a little bit out. And if you're interested in seeing that, it's not presented in your textbook, but Wikipedia is a good place to see those proofs. We'll look at 3.4 a bit more on Wednesday, and don't forget your templates, please, for the Pythagorean triangle templates. I'll see you then. So these you won't need until chapter 4.5. But since it is going to take a while, I just thought you could maybe make them ahead of time.